And so it's a pleasure to introduce our speaker tonight. Before I begin, though, I want to thank a retired faculty member of ours, a colleague, Carl Langenhop, whose generosity and his foundation has funded these lectures. And so we want to thank Carl once again for that generosity and foresight to fund this lecture series. Louis Kauffman received his BS from MIT in 1966 and his PhD in mathematics from Princeton in 1972. His research interests are in the field of cybernetics, topology, and the foundations of mathematics and physics. His work is primarily in the topics of knot theory and its various connections to statistical mechanics, quantum theory, and algebra and combinatorics. He studied in many places as a visiting professor and researcher, including the University of Zaragoza in Spain, the Institut Henri Poincaré in Paris, the University of Bologna in Italy, and the Newton Institute in Cambridge, England. He is the founding editor and one of the managing editors of the Journal of Knot Theory and its ramifications. He's the editor of the World Scientific Book Series on Knots and Everything. From 2005 to 2008, he was the president of the American Society of Cybernetics. And according to his Wikipedia page, he also plays clarinet in the Chicken Fat Klezmer Orchestra in Chicago. We're delighted to have him here, and it gives me great pleasure, and it is a privilege to introduce the 2013 Langenhop lecturer, Professor Louis Kauffman.
Special ceremony of exchanging microphones. I think that's it.
Okay. All right, I think you're ready to go.
Well, thank you. It's a pleasure to be here. The talk was originally entitled Virtual Knot Theory. There is something called Virtual Knot Theory. It's about knots that are happening inside of surfaces, and it's a slightly more technical version of knot theory than what I'm going to talk about today. I'm going to talk about knot theory itself, the basics of it, and background ideas in relation to applications of knot theory and in relation to the foundations of knot theory and how it relates to foundations of mathematics and other philosophical ideas. So this is a kind of broader brush stroke than what I had originally thought I was going to talk about, and I hope you enjoy it. Let's begin by looking. Oh, does somebody have one of those decent laser pointers? Anybody carrying one? One of the ones with a nice bright spot. I have one, but it's probably not worth using if it's not absolutely necessary. Anyway, you might look at my first slide here. It's a very well-known Escher print, or part of one, and it's a good introduction to topological thinking, this Escher print. What you have is a Mobius band, and it has some things cut out of it, like the parts that look like little circles are eyes, and you could ignore them for the purposes of the mathematical comment I want to make. And then also the Mobius strip has been cut down the middle in an artistic way. It's as though you took a pair of scissors and cut all the way along the middle of the Mobius band until you came back to where it started. And you may have done this yourself with a Mobius strip and a piece of paper. But if you look at this one that Escher has drawn for us and follow it carefully, or just look at it as a whole, you see that it's a knot. It's a trefoil knot. It wraps around itself and is actually knotted. And if we were to take an ordinary Mobius band, the one that you're used to, with a single half twist and cut it down the middle, you'd get one strip, just like you see there's one strip here. You follow through and there's exactly one strip, not two, but one, and it's knotted here. In order to get a knot, you need more twists. And in fact, Escher has drawn this or made this Mobius band with 3 half twists. one at the top. And I deliberately didn't bring any paper to do it because I think it's more fun. You should do it yourself. But if you take a strip of paper and put 3 half twists in it and then paste it back together and cut it down the middle, you get a knot. And you don't quite get the knot until, the final cut, and it opens up a little bit, and there's this knot, and you hadn't quite expected it before. On the other hand, you can see from here why you got a knot. I mean, it's sort of apparent just from the picture itself how you got a knot, and how also you got only 1 strip and not 2. But it's worth thinking about that. So that's an introduction to thinking about knots from the first slide. And here's one of the themes that I have for this talk, and that is topological connection and logical connection. We're familiar with the fact that for many, many years now, we understand logic better because we have things like symbolic logic and diagrams and Venn diagrams, which allow us to amplify our reasoning. And perhaps the most popular and well-known example of this is the Venn diagram, where if I want to understand different kinds of things about elementary logic, I draw a Venn diagram. Or if I have a bunch of propositions, I put them down in one Venn diagram and find out the conclusion from it. And what you're doing when you're doing that is using a geometric connection, a diagrammatic geometric connection, to amplify the logical connection that's involved. And this theme of topological connection and logical connection goes through and through lots of mathematics, and it certainly keeps reappearing in the knot theory and in lots of topological problems. Another example of this theme is graph theory, where Euler and the beginnings of topology, where Euler had a problem, which I also won't illustrate here, but it's a famous problem about traversing bridges in a certain town, Königsberg. And one was supposed to walk across all the bridges once and come back to where one started. There were islands, there were bridges, there were shores. And Euler abstracted the problem and said, well, there will be locations, and there will be some locations are connected to one another and some are not. And he didn't actually draw a diagram. He drew lists, names of locations, and which locations were attached to other locations, and reasoned on the basis of that. And probably not long after that, people began drawing such problems up with a topological diagram, which everyone is familiar with as a graph, where you draw points in a plane and you draw an edge from one point to another that indicates that they are connected to one another. And there you have exactly this theme. It's a logical connection between the 2 points, but it's depicted as a topological connection. Oh, that's great. Let's see if it works. I have more trouble seeing this than you do. Really, I do, yeah. Okay, I'll use it if I need it. So there's that theme. Now here's another example of that theme in action. We'll take this away for a moment. This theme is the relationship between discreteness and continuity. And in this little cartoon, you see this fellow holding a string, which is connecting 2 points, and it's a continuous connection between the 2 points. And then some kind of continuous deformation is going on here. And after a while, 2 little separate curls have emerged from the continuity. A plus and a minus have emerged discretely from the continuous background. And let's actually illustrate this so you see it happen. So there's the string, and it turns on itself like this. And then it goes underneath itself like this. And it goes underneath itself like that. And then it starts pulling apart, and there they are, the 2 opposite particles. A particle and an antiparticle, if you like, which when they interact can cancel each other out and produce just the continuous background. So So this is ample fodder for thinking about all sorts of things, isn't it? The relationship between discreteness and continuity, speculations about how particles and antiparticles might have emerged from a topological background. Lots of things to think about there. They're in the background of the rest of this. Now, you might notice that this is similar to twisting, but it's a little subtler. That phenomenon in the cartoon is a little subtler than twisting. But twisting also has this property. You see, I could take these two and twist them, and I could call that a +1, and then this would be a +2. It's the over and under, yeah. And then suppose I wanted to add -1 to the +2. Well, then I twist in the opposite direction. And then if I pull on this, those two in the middle will cancel, and I'm back to 1, right? So twists and opposite twists occur, and the topology of that is a little easier than what had happened with these curls in the cartoon. Now, one of the things that we do to make a theory about knots is to turn it into a kind of combinatorial theory about graphs. It's not the only way to go, but it's a very interesting way to go, and I'm going to be using it in the talk. What you see at the bottom of the slide are 3 diagrammatic depictions of moves that you could do on a bit of curve in 3-dimensional space that would be topological, that won't cut the curve or do anything discontinuous to the curve, but allow it to change. So in one case, we have a little curl, and that curl can be pulled off and removed or put back. In the other case, I have a bit of rope going underneath another bit of rope, and if you pull it slightly, they'll come apart. And in the third one, I have a bit of rope going underneath two other bits of rope that are crossing over one another. And then if you just slide that lower piece down a little bit, then it goes to there. I'm not flipping anything over. I'm leaving the endpoints of all of these diagrams fixed and just changing them in the middle because I have in mind to do something like that to a larger picture of some knot that I've drawn, like the one at the top. And so I don't want to make disturbances in the whole diagram. I just want to make disturbances in part of it. So it might look like this, for example. Simplest possible sort of example might be like this. You see, where, oh, that's good to know. Where if I were to use the move of type 2, I could change this diagram into this diagram by noting a two-sided region here and applying the second move. The second move says that if you have a two-sided region in the graph, and you have a double over crossing pattern in the graph, then you can remove the two-sided region. And that's just what I did, and you can think of it as pulling it out. And similarly here, this is by the number 1 move, turning into an unknot. So this is a diagrammatic sequence which shows that this parent knot is not knotted at all, it's unknotted. Simplest example that I could think of. But Reidemeister in the 1920s proved that if you take snapshots from 3-dimensional space of 2 knots, and then you ask the question, is it possible to get from one of those knots to the other knot by movement in space, by ambient isotopy, by moving the rope around in space without breaking it, moving it continuously, then if you can, then it can be done in the plane by a sequence of those moves. That's not quite obvious. It is obvious that if you do these moves, then the corresponding knots in space are equivalent. But Reidemeister proved that the entire problem of moving it around in 3-dimensional space can be accomplished by just moving it around in the plane after you've taken a snapshot. And that means that if we want to ask a mathematical question, are 2 knots equivalent, or is one given knot equivalent to the unknot, then we can ask it of the diagrams up to these moves on the diagrams. And so it's actually formulated as a certain kind of problem in graph theory. And you'll notice that the diagrams themselves are certainly not, as they stand, embeddings of rope in three-dimensional space or curves in three-dimensional space. But you know, because the diagrammatic convention is one of drawing, how to translate a picture like that drawn in the plane into a weave that you could actually make with a rope. You take the line which crosses over to be nearer to you than the broken line which crosses under, and that gives you the instruction on how to make the weave. So these diagrams are quite useful. And let's do another example of Reidemeister moves for fun. Tell me what you think about this one, whether it's knotted or not. What do you think? I think we could improve the focus just a little, but I'm not sure where the adjustment is. Well, never mind. Is it knotted or not? No. It's definitely unknotted. You can see clearly that it's unknotted by just grabbing hold of it and pulling it this way up off the page, and it all falls apart. The reason is the way I drew it. I drew it so that it was always going under everything I had drawn before, so it's descending. And if I draw a descending diagram like that, then it's quite clear that you can just pull it up and it's unknotted. On the other hand, Reidemeister's theorem says that it's possible to undo this thing by using Reidemeister moves. So we could look for some Reidemeister moves to do. Now the simplest move to look for would be the number 1 move, and you may be thinking, well, there's a number 1 move, but it's not, because I hadn't told you. But what I mean by these moves is that you will see a one-sided region in the graph, and then you can do that. But if it has other things crisscrossing through it, it's not a one-sided region in the graph. It's more complicated. So this loop over here is not an available 1 move by the game I play, okay? And a 2 move has to be a 2-sided region that you remove or put in, and the 3 move has to be a little 3-sided triangular region that you change. So going back to this picture and looking to see whether there are any 1 moves, we see there aren't any. And looking again for 2 moves, you see there are no 2-sided regions there. Here's a 3-sided region. Here's a 3-sided. Here's a 3-sided. That's 3-sided. This is 3-sided. Lots of 3-sided. That's 4-sided. This is 1, 2, 3-sided. And then the outside is many sides. So can't do any 2 moves. So the only thing you can hope to do is a 3 move. And then you have to look to see whether there's an interesting 3 move that you could do. And I see one immediately. But I'm used to it, so I recommend a 3 move that moves this arc. Now that's moving an overcrossing arc, and it's going to be of the form like that. See, sometimes I think of moving an undercrossing arc or an overcrossing arc. It doesn't matter. You could think of moving the undercrossing arc that way, or you could think of moving the overcrossing arc up. It doesn't matter. So that's what I'm thinking of, and then I'm thinking of the one that I put the blue dots on. So there they are. And you see, you could move that. Now I'll shade the whole thing blue. And I can move this little blue shaded arc up until it comes up over there. And if I did that, this is expensive in terms of time, and maybe we shouldn't. I think we shouldn't, to redraw it. But you can see that if you move the blue arc up, it would come up around there, and then there would be a 2 move that it is obstructing, and it would be gone, and it would no longer be obstructing the 2 move that wants to be made just underneath that blue arc. Imagine the blue arc is not there. Then there's a 2 move that wants to be made. So then you make it, and then it starts falling apart quite rapidly, and you'll see that it does. So that's a possibility. There are other examples we could give that are much harder, and I'll give you some very soon. Let me skip that slide. Here's an example that's much harder, actually. I'll tell you right now that it is unknotted. All right? And that although I have a little movie of that, which I didn't put into the slideshow, and I could show it to you afterwards if you're interested, I made the movie by using a certain physical model. And then I know how the movie works, so I know how it gets unknotted, and I can even visualize it. But I think that this would be very hard to imagine directly, even though it is unknotted. This is generally the situation. How do you tell whether a configuration like this is knotted or not? And by just having it in front of you and looking at it as a rigid geometrical object, it's very hard to tell how you're going to go from there to something else that would be simpler. If it were easy to tell by just looking, there wouldn't be any need for a theory. But in fact, it isn't easy to tell. And one of the things that people who study knots do is they work on ways to calculate things from a picture like that, from a snapshot like that, and to calculate things that will be properties of that don't change when you move it around. And we'll see that later. But if I could find some property of that didn't change when it got moved around, and if that property didn't belong to the unknot, then it couldn't possibly be knotted. So we'll see. Here's another knot diagram. But this knot diagram is actually an electron micrograph of a protein-coated DNA molecule. And the people who did this, Stasiak and others, in the 1980s, had the aim to find out whether or not DNA was knotted. They believed it could be knotted, and they wanted to prove that it could be knotted. And so they developed a technique for coating the DNA so that when they took an electron micrograph, they could see the DNA molecule going over or under itself in the picture. So if somebody just gave you a picture like this, looking a little fuzzy, you might not be convinced that it represented anything knotted, but it is known that this is a DNA molecule and it was coated with protein, lots of collateral information about it. And with that in mind, biologists were definitely convinced that what is happening here is that it's going over up there and then under and then over, and in fact it's alternating over, under as it goes all the way around, and it's making a knotted curve. And so this was regarded, and still is regarded, as proof that DNA can be knotted. And there's lots of collateral evidence about that. For example, biologists use gel chromatography and watch the speed at which the molecules move down through the gel. And the ones that are purportedly knotted move much more slowly than the ones that are unknotted. So there's lots of evidence and collateral evidence that DNA can be knotted. And on the other hand, it is a knot diagram. So this is an example of how knot diagrams, in the sense that I'm using them, are actually useful in science. And that you wouldn't have been able to do it without the knot diagram in some sense. You wouldn't have been able to see that. Let's continue with this a little bit. Here's the knot tables. Can you figure out, I rotated it just to make it a little easier to look at. So what you see when I say rotate is the very same photograph, it's just been turned around. Okay? Can you find out which one of the knots on the table, this is part of the knot table, the first few knots, can you find out which one it is? a hint. It's in the first row. Which one? I'll point. I'm not sure I heard correctly, so let me try. Oops. There. And then, where's the... Okay. So, which one were you saying?
There are several votes for 6-1, 6-2, and 6-3.
All right.
And not 7-1.
Certainly it's not 7-1. What do you think? It's one of these? Which one? Well, let's see. Might it be 6-1? If you look at 6-1, you see, well, no, there's a loop in the middle that comes down around like that, right? There doesn't seem to be any loop in the middle there, but look at 6-2. Loop in the middle, over, then under, then over, comes back up, goes over, then it wanders this way a little bit and it goes back under, then it goes back over, right, and comes back down around and through. Looks like 6-2 to me. It's 6-2. And you see, you have to think like a topologist in order to say that it's 6-2. That is, a topologist in the popular definition, a topologist is someone who doesn't know the difference between a donut and a coffee cup. Right? You have to use that definition of topology in order to see that it's 6-2. Oops, sorry. Okay. Now, there's a lot of other knotting and geometry involved with DNA that's worth thinking about. This slide is just meant to stimulate. I won't go into any details, but DNA is a double helix, 2 strands, and it winds around histones, and they supercoil and pack and wind into the chromosome. And people don't know really that much about the geometry after a certain point. This is an artist's representation. It makes you think that, well, it's understood all the way out to there, but it's not. And it's not really well understood even how it comes about that DNA could manage to reproduce itself. Because you see, you have these 2 strands which are wound around one another, many, many windings. And DNA reproduces itself by breaking the bonds between the 2 strands. There are enzymes that do that. And then the strands are hanging out there in the cellular environment with their bonds broken, and other molecules can come in and form new base pairs, 1 for each strand, and then you get 2 strands, 2 double strands, right? And then you have 2 double strands which are wound around one another if there weren't anything else happening. And they wouldn't come apart. They would be interwound just as much as the original DNA was, only you'd have 2 DNAs all wound around one another. So the cell wouldn't be able to reproduce. So this was a problem which was begun to be solved around the late 1970s by Wang and his collaborators at Harvard. And they discovered that there are enzymes which will walk up to the DNA and break the bond and allow the other DNA to slip through it and then put the bond back together. So that means that it's like this, that you have 2 things that are linked, and an enzyme opens that linkage up, and then the other one can float out, and then this gets reattached. And if you did this with a link with one component, like with one wind, like this link that I made with my fingers, well, then you could unlink it with one operation. But in order to get the DNA to come apart, this would have to happen thousands of times. But there are enzymes that are there and that are doing it. And so people believe that that, in fact, is what's happening. But how it's orchestrated exactly is not understood. There's real topological problems down there that are being solved by the biology. this talk is not entirely about DNA, but I had a few things about it that I wanted to talk about at the beginning. Here's another example of relationship with DNA and knot theory. You see here a schema for a DNA molecule that's not knotted. It's just got some twisting in it. And this is meant to be the double-stranded thing. And you don't see the two strands. You're just seeing a schema. All right? And then you imagine that it moved around and came close to itself over there. And then there's an enzyme that comes along and cuts it and then recombines it like this. So it cuts the strands and takes a strand from the upper part that's cut and attaches it to the lower part that's cut, and vice versa, so that it goes from being a little cup and a cap like that to a crossover. And that's a recombination. Now, one thing that people didn't know was which handedness of crossover occurs. They believed that in these simple recombinations, it did just cross over. You could imagine that it did something more complicated, like twist a few times and then recombine. Well, that would make a much more complicated connection. It could happen, but in this kind of experiment that they were looking at, they believed that it just crossed over. But you would get a completely different topology if it crossed over this way than if it crossed over this way. Here I've illustrated that it's crossing over from upper left to lower right each time the recombination happens, uniformly each time. So the first time, it went from being unknotted to being a simple link. And the next time that it happened, assuming that it happened right nearby like that, it went over and turned into a figure-8 knot. And then the next time, it turned into another link. And then the next time, it turned into another knot. And you could imagine an experiment. In fact, people can do an experiment where you do have processive recombination like that. It recombines, then it recombines again, and it recombines again. And the most likely products are ones that are right near one another like that. And then you can look at the products, and they did, using the electron microscope technique. And they discovered that they got, in this particular experiment, they got this sequence of knots. Maybe they didn't know about K4, but they could see the others. And that's pretty good evidence, just on the basis of very elementary knot theory, that it was this handedness and not the other, and that it was uniformly that handedness. So this is an example of an interaction between knot theory and biology. It led to other questions because the topologists can ask, suppose that I know that some black box method of recombination, that the little crossing there that I'm putting in is unknown. I don't know what it is that I'm putting in there, but I know that I'm doing it 4 times, and each time when it's done once, I get this link. When it's done another time, I get that knot. And when it's done a 3rd time, I get this other link. And I don't know what the internal structure of the thing is. Then I have an unknown and 4 equations for that unknown, topological equations. And you can try to solve the topological equations and prove that it had to be the right-handed single twist. So under some hypotheses, you can do things like that. And it leads to problems that are good for topologists. Here's another aspect of things. This is the magical aspect. So you see that what's being made here is a simple square knot, and now it's being made a little more complicated, and then a little more complicated. And the question is this knotted or unknotted? But we're about to find out. So this is quite reproducible. Let's do it again. I make a simple overhand knot, a trefoil knot, and then I make a square knot above it by making another weave like that. So what you're looking at now is a square knot with the lower part connected up, and then I make it a little more complicated by dropping the line through the bottom part here like that. And I assure you this is knotted. It's the next part that I say, if I'm performing it as a magic act, that I've made it even more complicated. But in fact, this threading has undone it. And it's not obvious when you're making something like this and then threading again that you might undo it. You might undo it, or you might make it much more complicated. I don't know a good theory for figuring out when the next threading is going to simplify it, but this is simplified. It's not knotted at all, even though it looked knotted. And that's a well-known magician's trick. There are variants of this that are interesting. I'll show you one more just for fun. Let me see if I can do it. Yeah, I hope. I like this one because it seems even more incredible that it would be unknotted. What you're looking at here is a knot a little farther up the knot tables, but you see it's a phenomenon of knotting that's interesting. I have a simple overhand knot, and then I have another overhand knot, and then they're clasped to one another, right? Higher order linking involved between the things that are already knotted. It's very knotted, and of course we haven't proved that, but it is. This is definitely knotted, and all I do is I drop that line through the left-hand one like that. Now, I don't think anyone in his right mind would think that that was unknotted. You'd have to analyze very carefully to begin to see that that was unknotted, but it is unknotted, and I will prove it. What I'm doing is a mathematical proof, mind you, right? At some level of proof. I mean, could this be any more certain than a proof written out line by line by logic line, that knot was unknotted? The only thing I need to do to turn it into a formal proof, in the sense of the Reidemeister moves, would be to watch slowly and carefully while I do it and make sure that I've factored it into little Reidemeister moves, and then write the whole sequence of pictures, diagrams, graphs carefully, one to the next, to the next, to the next, and you end up with a sequential proof. So one of the things that I find curious to think about in relation to topology is that sometimes we can generate proofs by going into the analog domain of physically moving something and find that something is surely true, and the certainty of that proof that I just did with the rope is no less certain than the one by step by step by step. It is at the same level of certainty, but it involves using something physical which I don't know how to formalize completely unless I break it up further. And I can break it up further into the Reidemeister move. So proofs can be physical and completely convincing. That's just a picture of where we started. And then here's another one, which I can do also, but I'll just let the film do it. You put a ring on it. And then we're going to do everything we did before, almost. That's as we had it before. And then I'm going to thread through the ring to make it possible for the ring to drop off by making sure that there isn't any total linking with the ring. And then the rest of the threading is very similar to the threading we had before. If you do it even slightly wrong, it won't work, of course. Now it's definitely unknotted, but is the ring going to disappear off the rope? Yep. The ring didn't disappear, it just disappeared off the rope. So that's a next step in terms of the magic. The magic can be simple. There has been no sleight of hand in that magic. It's just topology. There are other versions of the magic where there might be something else going on. For example, I can tie a knot for you. And it's nice, perfectly good knot on the rope. and then I use my access to the fourth dimension and it disappears. So that's a different aspect of using the magic. Now another vignette. This is going in the direction, still in the direction of physical knotting. It has been a long time a question whether a person could blow a knotted smoke ring. This YouTube movie shows that dolphins know how to make rings, vortex rings, or have been somehow coaxed into or trained to make these rings, but it must be natural for them. They shake their head in a certain way and they get a vortex bubble ring in the water. This comes from some aquarium. I'd like to investigate this further and find out more about it, but you can find this on YouTube. And you can blow, and you may have blown, smoke rings by moving the air past your lips, formed in an O shape, and the smoke, and you get vortexing around coming from the edge. You blew the smoke past, and you get rings, smoke rings. But can you blow a knotted smoke ring? Or if not you blowing a knotted smoke ring, could we make an experiment where a knotted vortex was created? This has been an open problem for some time, until recently when Bill Irvine and his collaborators in Chicago have done this. They have made knotted vortices in water. And I have a film of this to show you. This is a picture from their paper, which I'll talk about for a second so you can see what they do. If you wanted to make a vortex ring, you can do it just like a smoke ring and have an open hole and push the water through the hole, and it will vortex, and you'll get it with little bubbles. You'll see little bubbles, and you'll see the vortex ring. They made a knotted frame to push the water through. That might seem like cheating, but I mean they really made a knotted vortex by doing it, and they pushed the water past the knotted frame. And then you get a vortex ring propagating beyond the knotted frame. I'll show you the film in a moment. They make those frames by using a computer to generate the shape of the frame, and then a 3D printer to create these frameworks. So it's modern technology creates knotted vortex rings. Now this one is the unknotted ring coming from the first type that you saw in the previous slide. And here's the knotted one. I'm going to go back and do that twice. You see it only for a moment, the knotted frame in this film. I think it's a great experiment. I don't know what will come of that, but it's an amazing experiment. Now, knotted vortices have, for a long time, been a speculation. Lord Kelvin, back in the 19th century, thought that atoms, people were beginning to understand what atoms were. He thought that they might be knotted vortices in the luminiferous ether. And it was thought that, the background in space was a fluidic ether, and so it's possible to have knotted vortices in it. And he investigated knotted vortices quite a lot because of that. And that theory died away along with people not believing in the ether after a while. But people continue to think about knotted vortices, as you see, and probably one of the effects of that research at the University of Chicago will be that there will be more people looking at the mathematics of knotted vortices. next item is the Dirac string trick. Now, I think I forgot to bring another belt, so we'll use this one. The Dirac string trick is a phenomenon that you can see with a belt. If you would hold the end of that, please. Now, what I have in mind here is that the belt is attached to a reference frame, and that's Greg, and it's also attached to a ball, which is hanging in midair so that the belt can be brought around the ball. Now, in order to do that, I have to do something that looks like sleight of hand because I want to bring the belt around my arm. But my arm is in the way. I want to bring it around the ball. So what I'll do is I'll exchange hands. When I exchange hands, I'm not going to rotate this. So nothing is happening. It's just getting out of the way. That's all that I'm going to do. So if I twist this by, that's one full 360-degree twist and then one more, then it's been twisted by 720 degrees. And if I bring the belt around the ball and see what happened, you see that all the twist is gone. That's the belt trick. Now, if you ask yourself, why did that work just on physical grounds, you can see that what happened. You can see what happens if you twisted it only by 360 degrees. Now, I twisted it in a clockwise manner to make the 360-degree twist. And when I bring it around my hand and look at it this way, it's now twisted by 360 degrees, but it's twisted in a counterclockwise manner. So it transforms clockwise to counterclockwise and leaves it at 360. That's what happens physically. So then you see what would happen if we had 720. I have 1, 2, 3, 4. If I did that and I only took half of it, maybe you could bring your hand out and hold it right there. Yeah, keeping that. So he's protecting that twist, and I'm taking this one around. It turned into minus 360, but now you have plus and minus, right? Plus over there, minus here, and when he releases his hand in the middle, it's all gone away. So that's one way of understanding physically what happened. Thank you. So that's called the belt trick, and it's called the Dirac string trick because Dirac used to use it to illustrate the properties of a fermion, of an electron. If you, as an observer, were to walk around a thought experiment electron, say this green chair is an electron, you were to walk around it slowly and come back to where you started, the wave function for the electron will change sign. That's a fact of quantum mechanics. And that means that a 360-degree rotation isn't the identity in quantum mechanics. If you take an object and look at it quantum mechanically in relation to its surroundings, an observer in relation to an object, it isn't going to be back to where the world is not back to where it started if you go by 360 degrees. But if you go by 720 degrees, twice 360, then you're back to where you started. The reason for that has to do with the fact that in quantum mechanics, rotations or any other motions, processes, are represented in the unitary group. And I won't go into that, but unitary matrices have to represent the process. And if you try to represent a rotation into the unitary group, it ends up not coming back to where it started. It comes back somewhere else. And the simplest example is the case of ordinary rotations around axes in three-dimensional space, where instead of coming back to where you started, you come back to the negative of where you started in the unitary group. Now, I don't want to go into that, but I can show you how the algebra works by thinking diagrammatically in 3 dimensions about the belt. And it goes like this. We're going to have 3 operations called I, J, and K, which are, first of all, just rotations in 3 space. And I is going to be rotation by 180 degrees around the axis pointing out of my body. And J is going to be rotation of 180 degrees around the axis parallel to my body. And what did I say? I always say this wrong. J is going to be, I is this one. J is this one, the 180 degree rotation around the axis parallel to my body. And K, the resultant, is the one that's 180 degrees around the axis parallel, okay? So if I do I and then I do j, I get k. That seems normal enough. But if I do I and then I do j and then I do k, I end up, because I'm watching my body, I'm watching the object that I'm rotating in relation to its reference frame, I get a twist of 360 degrees. We could do the same thing with the belt. In fact, maybe we should. If I take the belt and I rotate it, let's do it the way I was saying. I'm going to turn this by 180, and then I'm going to turn this way by 180, and then I'm going to turn this way by 180, and you see I get a 360 degree rotation on the belt. Okay? So what I said could be made objective or personal, depending on whether I want to do it with my hand or with the end of the belt, and rotating around different directions in space. Thanks. But what I'm saying is that there is an algebra there of I and j and k, and what you see is that what about I squared? Well, if I do I and then I do it again, I have 360 degree rotation of my arm. Now, why do I say minus 1, or did I yet say minus 1? I say I squared is minus 1 and j squared is minus 1, and ijk is minus 1. You saw ijk, 360 degree rotation. The 360 degree rotation is minus 1. But why do I call it minus 1? Because if you do it twice, it goes away, right? It's the 720 degree rotation. So we're identifying 360 degree rotation as minus 1. And then we have I squared equals j squared equals k squared equals ijk equals minus 1. Those are Hamilton's quaternions. And that structure is actually the unitary structure that happens in quantum mechanics. And so when you attach an object to its surrounding, you double everything. If you made a 360 degree rotation of the object, you get this twist, and it stays around. But if you take a 720 degree rotation of the object, you're back where you started. The twist is topological, and so this topological connection becomes the logical connection that expresses the algebra of the quaternions. When Hamilton originally invented the quaternions, discovered the quaternions, he didn't know about the topological connection. People discovered that later. And this is a rather intriguing one in that it is genuinely turning topology into algebra at exactly the right point so that this works. And it, of course, leads to the question of what it could mean that this is really happening for things in space like electrons. Some people naively think, and maybe they're right, that there's some property of space that's really like this, and it's every time you turn by one more thing, it's twisting and untwisting. And others think it's a mathematical structure that is just part of the description. I don't know. This is just the cartoon that illustrates what we were saying. If you want to see a whole set of those cartoons, you can look in the book I wrote, Knots in Physics. And here's a little film we made a long time ago that illustrates these ideas. But if you rotate it in the right way, it won't. You see, I keep turning this, and the belt is not getting twisted up. And that's what you're seeing in the film also. And it has to do with the fact that I pass the buckle over, and then I pass it under, and then I pass it over. But I can keep something rotating this way as much as I like, and it just keeps flipping. Twisted, not twisted, twisted, not twisted. And this one is something you might have done yourself. Like that. And here's the belt and its surround, and 720, and then back to nothing. And you can have as many things connected from the inner sphere to to the outer reference frame as you like. So this is a film that we made at the Electronic Visualization Lab, George Francis and Dan Sandine and many other people helping a long time ago. How are we doing in terms of time? We have no time, or I'm not sure. Let's see.
Yeah, it really depends on how many questions you want from the audience.
Right. Let me talk for another 5 minutes or so, and then we'll take questions. Okay, it's a rich subject, and there are many things you can do. This is illustrating Reidemeister moves again, and a favorite link that I like called the Borromean rings, sometimes called the Ballantine rings. It's 3 rings, but if you remove any one of them, it falls apart, as you see. So from a logical point of view, it's a tripartite relation, right? You need all 3 of them in order for the relation to happen. This is a relationship that I find very amusing, and it's the beginning of a whole series of relationships between knots and physics that go through the diagrams. In this case, what I'm doing is I'm shading the diagram, and then I'm replacing the diagram by a graph where each region that's shaded has a node, and every time there's a crossing between the 2 regions, you get an edge. And maybe the middle one is a good one to look at. You see there would be a node on the left, a node on the right, and 2 edges going through because there are 2 crossings. And then the edges are labeled plus or minus according to whether it's from top left to lower right or from lower left to top right in the crossing. And then you get things that look like electrical circuits. And Jay Goldman and I realized that it isn't that they just look like electrical circuits, they have all the right patterns for electrical circuits. If you interpreted plus and minus as conductance, and that means that minus is an amplification, and plus is a conductance of +1, inverse resistance, then these are correct identities in calculating the conductance of the resulting electrical circuit. That means that if you were to take a knot diagram and shade it and put a terminal here and another terminal over here and measure the conductance of it as though it were a complex resistor, complex conducting circuit, that would be a topological invariant of the knot. It wouldn't change when you move the knot around topologically. So it's a relationship with the physics. The Reidemeister moves are somehow mysteriously related to physics. They are mysteriously related to physics in a lot of ways, not just this way, and we don't understand it. Then I'm going to introduce you for 2 minutes to what I call knot logic. That was the title of the talk, but I also call something specifically knot logic. But it has to do with the ideas. Taking those ideas at that level. So for example, the Borromean rings have a peculiar logical property aside from being tripartite that I think is worth remarking on, and that is, look at it. Green surrounds red, but red surrounds blue, and blue surrounds green. And if you weren't trying to make a mathematical model in great detail, you might be convinced by that alone that that had to do with the fact that they're linked. It surely does, but when we try to make it more technical, that remark has a tendency to disappear. They are a scissors, paper, stone pattern in topology. Then there's Buckminster-Fuller's remark that knots are patterned integrity on the substrate that carries it. The knot is a pattern that's independent of the substrate. It can persist while the substrate is changing until it's no longer the same at all. Something like this, that we have this substrate, but another substrate is coming in, and eventually that substrate subsumes the knot completely, subsumes the knot completely, and the knot is now living on an entirely different substrate than it was before, but the knot has persisted. From the point of view of what topologists do, that's what they do, right? They ignore the substrate. But if you're thinking of it as an analog for biology or other systems, then it's remarkable to understand that it is a pattern which can be completely independent of the substrate, like a biological pattern like us, where material is continually flowing through us, but our pattern remains to some extent throughout. And then there is the stability of something as simple as a trefoil knot. One loop isn't stable, but one loop linked through itself with another to make in all three loops becomes stable. And that's interesting. And then I like to make a version of set theory out of knot theory for the fun of playing with the foundations. So when I do that, I let one line going underneath another be a member of the one that it's going under. So this is just a definition. If this line is underneath this one, I shall say this line is a member of that one. And then you will have some curious sets. You will have some sets that are members of themselves, and you will have chain linkages of sets, and you will have mutuality. You will have A as a member of B and B as a member of A, quite naturally in this notation. The notation amplifies the possibility for non-well-founded sets. And it can also be used to indicate some standard things. Like what I've labeled 0 has no members because it's at the bottom of the stack. And 1 has as its only member 0. And 2 has as its only member 0 and 1. And 3 has as its only members 0, 1, and 2. And this is a famous method for counting due to von Neumann, which in this way of drawing it is almost palatable. And then there's Russell. After all, A could belong to A or not, according to the first Reidemeister move. So it seems that you get a different take on the Russell paradox when you look at it this way. That's just another picture of the set that's a member of itself. And then you have to think about the topology of this. I don't want to go on too long, but you see, if I have one curve which is going twice over another and subject to a second Reidemeister move, then I would have that B has a couple of members, 2 copies of A. So multiple copies have to be canceled in pairs. It's not the usual rule. You usually condense multiple copies. You say if I have A and A, then it's just A. But here, you have to let them cancel in pairs to do this set theory. So you could say it's fermionic. And knots are not seen by this set theory, so we have to do more to see knots. And this set theory is interesting to play around with. I'm going to jump across something and end the talk with some pictures. So let me jump across that and that and show you a 3-colored trefoil knot, colored with 3 colors. We're going to end by proving that the trefoil knot is knotted, and I hope it convinces you. So here's a trefoil knot. It's been colored with 3 colors. A is, I won't try to describe those hatchings, but A and B and C. And I'm going to have a rule for continuing these colorings. The rule is 3 colors at a crossing, like you see here, or only 1 color at a crossing. You can see why I would want 1 color at a crossing sometimes, because if I did a little twist, a little one move, why then I could leave everything else the same as long as I just kept it to be 1 color. So that's the game. The game is that I want to persist the coloring and either have 3 or 1 at a crossing. So I'll try to do that. I'll move it around. I push it under with a 2 move, and I see, oh yes, I can use the 3rd color there, and it's still colored. And then I do another 2 move, and use the 3rd color there, and it's still colored, and there, and it's still colored. And now I have the same color going up to the same color, and I want to do a 2 move. And so I use the 1 rule, 3 or 1, not 2, just 3 or 1 throughout. And then I have a 3 move there, which is that little upper triangle at the top. And I'm going to do a 3 move by sliding it under. And that's what happened to get from upper right to lower bottom, to the middle bottom. And then you see that it was compatible. I could keep a single color in the lower crossing, and then it changes to 3 at the next one up. And I only changed the one little arc, the one arc of the triangle, and this is three colored. So what you get, I'm sorry?
Your laser pointer, is it?
Laser
pointer.
The laser pointer? Oh, yeah, it doesn't help very much, but let's try. Okay. So you see, there's the three move. There's the triangle for the three move. And this little arc is going, and I'm going to slide this arc here under, and it ends up over here. Everything else is the same. And all the colors out here are the same, and the color coming in is the same. This little arc becomes this little arc and has to be recolored. And it got recolored to be the same as this and then different. And we got three here and one there. Okay? So that's what I did. And then if you check, you'll see that this will always work, just like that. A couple of other cases. You can keep on doing Reidemeister moves, your heart's content, and wherever you do it, it will prolong the coloring of the knot to a coloring of the new one. Make it more complicated, make it simpler. It will always stand there having three colors on it when you started it with three colors. It requires a little thought to see that you will never lose a color. I'll leave it for discussion, but you never will. And so that means that as we move the trefoil knot around, the property that it retains is the number three. Three colors. And so it can't possibly get to the unknot because the unknot can only be colored with one color. There's no way to color an unknotted circle with three colors. It's just got one arc in it. And therefore the trefoil knot is knotted. That's the simplest proof I know that the trefoil knot is knotted. And it does that. What it does not do is prove that the trefoil knot is inequivalent to its mirror image, which would be the next thing you would like to know about. You could go back to a picture of the trefoil. If you were to switch every crossing in that picture, you'd get another trefoil knot. But it's a left-handed trefoil knot to the right-handed one that you see. And there's no way to topologically deform one into the other, and that requires more proof. The next level at which I know an elementary proof of that is the Jones polynomial, and that's a polynomial invariant of knots and can be defined, and if we were going to continue for another hour, we would do the basics of the Jones polynomial, among other things we could do. But we'll stop here. So you see, it's not so easy to check that something is knotted, but sometimes there are very nice ways of thinking about it combinatorially. More generally, the subject is, this topological subject is very close to the foundations of mathematics because of the way we are looking to represent it, and when we use diagrams particularly. And so there are many, many general issues and many ideas that are coming up when you're thinking about this that you might not have realized would come up when you began with a simple topological problem of trying to understand whether a bit of rope is knotted or not. I'll stop there.
Any questions for our speaker?
Yeah.
Back when you had your 6-2 DNA piece, now the DNA can't be a Mobius band, it has to be an annulus, right?
It can't be?
A Mobius band.
As far as I know, it can't. But I don't know whether it can't or whether people have never seen that. Yeah. It should be protected from being Mobius. Yeah. I have to tell you an anecdote. I met a postdocing biologist many years ago who thought that maybe it could be a Mobius band and that would be part of the processes. But I don't think she ever convinced the experimenters to prove or disprove that. And I don't know what's happened in the intervening years.
In this non-standard set theory model, can you represent something there like axiom of choice or axiom of determinacy? Can you represent something there that's slightly more exotic than the things you drew?
Well, what I've done is not very propositional. It's more at the very low level of representing sets in one way or another, like with brackets or with not with brackets or with a diagram. If I start making statements like from a given collection of sets, I can choose one from each and make a new set. I can look at how that would work diagrammatically, imagining choosing lines from all of those different things and bringing them together into one bundle. So I would be thinking like an electrical engineer if I were thinking that way in these diagrams, that the axiom of choice would be sort of metaphysical electrical engineering. But I don't know if it has any good consequences to think that way. On the other hand, if you were thinking about things like braiding and you started to think about braids with infinitely many strands, then you would get into, set theoretic questions, and you will.
Any other questions?
Yeah. Using this analogy between knots and electric circuits, can you solve a problem in knot theory by just building a little circuit and sending a current through it and see whether the bulb flashes or not?
Well, as I said, I can solve the following kind of problem by building an electrical circuit. Suppose that I take the figure 8 knot and I checkerboard shade it. And then I build the appropriate circuit. And then let's say that I connect this up to a battery and a meter. And I measure this, and I find that it has a certain non-trivial current, right? And it's positive and not negative, perhaps. Then it tells me that I couldn't, holding on to these two terminals, turn that knot into its mirror image. And that's what it tells. Of course, I don't have to actually build the circuit to know that. All these crossings have the same sign. Well, maybe they don't. They don't, probably. But if they did, and it was positive, I couldn't turn it into its mirror image holding these. Because when I turn it into its mirror image, it switches all the signs. All right. So I can use that. Now, I've used that in the following way. I had a program that electrical engineers use to compute conductances. So I would, in fact, make the graph and then hand it to the program, and it would figure the conductance for me, and then it would tell me something about the knot. So you could, in principle, do that. I used to think for other things, there's Witten's functional integral, which is some more complicated physics. And I used to think, well, we'll have to have this device where we put the knot into a gauge field. Well, it'll be like a microwave oven. We'll put the knot inside this device, and it'll be in a field, and then the machine will tell me something about the knot. You can try to visualize physics which actually is just in your head. Does that answer your question? I hope. I'll give you another example. Let me push forward here. I'm sorry, I'm slipping things past. But there's a related thing. This is in the opposite direction. Here's a problem for you. Design a switching circuit that can control a single light from an arbitrary number of locations. Now, if you teach Boolean algebra, maybe you don't, but if you teach Boolean algebra, you know that you can design circuits of this kind by writing down the logic and then turning it into a circuit. But this is for n lights, and I want a design that will work reasonably and won't turn into some exponentially exploding number of switches and things like that. And if you do it the usual way, you'll find that it's going up exponentially. So what are you going to do? This solution that I'm about to show you is due to Ricardo Uribe, who who like to tell this to his design classes. You make a switch, which is like everything else we've been talking today, two lines parallel or crossed over. That's it. Those are the two states of the switch. So that means a signal can go along this way and another signal can go along this way, or when it's in the other state, the signal goes down here and the other one goes up here, permutes. And then you see that if we had one switch like that, it would, when it's Mobius, the light is on, and when it's not Mobius, the light is off. There's no band. There's only the line. And when these cross over, they don't really cross over. They're just like a knot crossing. I should have manipulated the diagram a little bit better so it would be just an over and an under crossing. So then you see Mobius or not depends on whether there are an odd number of switches thrown or not, right? Where thrown means crossover and unthrown means no crossover. So if there are an odd number of switches that are thrown, it's Mobius. If there are an even number of switches that are thrown, it's not Mobius. And so whenever you walk up to any given switch, whatever the configuration, it will change the state and turn the light on or off. So this is using topology to solve an electrical problem, the opposite of your question.
Is 137 the subtle constant?
Oh, well, yeah, I thought 137 would be a good number of switches to use.
Lamar?
You kind of browsed through the sets when you talked about a little set theory. My question is, can you use set properties of sets and set theory to solve knots, or maybe even do some of the transformations that you were doing with the knots?
Well, in that set theory, how did this become pink?
It happened in the middle. I have no idea
how. I started drawing pink color. Well, it doesn't matter. The fact that this is a non-trivial pair of sets essentially is implying that link is linked. So some very elementary properties of linking are being implied by those sets. But the sets all by themselves are a rather weak picture of the knot theory. You can try other things, though, that are sort of similar. For example, you know that a category is a mathematical structure with objects and morphisms, right? And a knot diagram then is generating a category, but there's something peculiar going on here, because if you looked at the arrows in the knot diagram as somehow like morphisms, then the objects are also the arrows. So now, of course, in category theory, almost anything goes, so I couldn't call that a non-standard category. It's just a category that has the property that its objects happen to be morphisms. So knot diagrams are generating categories that are reflexive in the sense that their objects are morphisms. And in that case, I think that those categories actually contain a lot of information about the knots. I've been thinking about that, but I haven't got it to the point of writing a paper about it yet. All right. So that's similar to asking whether you can prove things using the set theory that would be strong. But the set theory is more meant to be a kind of, for me, it's meant to be a kind of an illustration of the epistemology of this thing than a technique.
Any other questions? John?
Back there.
The Russell slide?
Yeah, you want to go back to the Russell slide? Yep. There he is. Oh, you're taking a picture of the slide. I can give you I can give you a PDF of the talk too. Yeah. As long as we're back at the Russell slide, That symbolism in the little box is one that I happen to like. You may know it. Comes from some versions of logic. Rx means X is a member of R. That's just the definition of it, all right? That's what Rx means. AB means B is a member of A. So then I can write the Russell paradox very concisely. X is a member of R means that it's not the case that X is a member of X. Once that's written down, then the paradox emerges without having to go back into language and torture yourself. Because you say, what if X was R? And then you get R is a member of R is equivalent to it's not the case that R is a member of R, and that, of course, is the paradox, unless you lived in a logic where negation could have a fixed point. But that's another non-standard direction, right? You could imagine logic where you have true, false, and something else, which is left fixed by negation. Neither true nor false. Not neither true nor false. Maybe it means the same thing. So in such a logic, you also wouldn't have the Russell paradox. I have to be careful or I'll be digressing again, so I'll stop.
Let's thank Professor Kauffman.
Thank you.